All right, so our first podcast of the unit stopped right around here. And so this podcast, or this video recording, is going to pick up where that left off and just finish out talking about these Bronsted-Lowry definitions of our acids and bases and how we can use that to identify our conjugate acid-base pairs. And the first thing to do is to remember what the definition of a Bronsted-Lowry acid and base are. Acids are always proton donors, and our bases are proton acceptors. And what we have written here tells us that those acids, those proton donors, are going to be turning into conjugate bases when the reaction happens, and bases turn into conjugate acids. And it's really weird for some people to remember, and hard to remember, that these things are switching jobs. It goes from an acid to a base, and how does that happen? And isn't it always an acid? So I have a little visual here to help you kind of understand what's going on before we actually get into those examples down below with kind of weird looking chemical formulas and equations going on. So this visual is just using some colored shapes to help us understand what's happening to our acid and our base when they react together. And so I'm just using these kind of squares to represent our acid and base, and I have made an H+ circle there just because we know that part of our acid is going to be moving and changing, but that's really the only part of our acid that's going to be moving and changing. So that's the only part that I made stand out. So, like Bronsted-Lowry says, when this reaction does occur, our acid is going to transfer that proton to the base. So that donating and accepting is happening at the same time. Our acid donates directly to that base. The base accepts the H directly from the acid. And now we have formed our products. And the products are always going to be called some kind of conjugate. And we'll talk about and reinforce whether they're acids or bases. But for right now, we just need to recognize and understand that the products are always going to be the conjugate. The normal acid and base, just plain old acid and base, will always be our reactants. And so right now, I have a red conjugate and a blue conjugate. The red conjugate started off its life as the acid. The blue conjugate started off its life as the base. Now, what conjugate means is that this is not just a product, but chemical reactions are in fact reversible. And so if I reversed the direction of my reaction, then my products would be reacting together to form what we previously called our reactants. But now really the products are the reactants, and the reactants are our products. So our reactions can be reversed. And I know that that's kind of a weird idea for some of you, but it does happen. It is completely okay. And even though your elementary or middle school teachers tell you, oh, physical changes can be reversed, chemicals can't, they can. They lied to you. Chemical reactions can and do get reversed all the time. So if we reverse this reaction, the opposite of what happened in our forward reaction is going to be happening, meaning that that H+ is going to be moving from my blue conjugate to the red conjugate. And when that happens, because our blue conjugate there is donating an H+ to the red conjugate, that means it's acting like a proton donor, and proton donors are acids, which means that when we name that conjugate, it's not just a conjugate. It is the conjugate acid, because if we reverse the reaction, that thing is going to be acting like an acid. Even though that was the blue conjugate, it started off its life as a base. When we reverse things, it's acting like an acid. So when we reverse the reaction, everyone's roles reverse. The acid turns into the conjugate base, and conjugate base is just a fancy word we give to that product that tells us, well, right now it's a product, but if we reverse that reaction and it did react, then that conjugate, that substance, would be accepting an H+ and acting like a base. So the jobs of our chemicals flip when we flip the direction of the reaction. And honestly, that idea isn't that complicated. It's just we're doing it with these complicated chemistry ideas, and it just really sounds impossible or weird, like we're breaking science when things are switching jobs. But even just two people tossing a ball back and forth, whoever starts with that ball is automatically the thrower. That's the only thing they can do in this very simple game, is if they've got the ball, they throw it. That means the other person is the receiver. They're catching the ball. But as soon as that happens, if we're going to keep playing this game, and we're going to have to reverse what is just happened, do the opposite, and when the ball gets thrown the other way, the person that started off as the thrower is now the receiver, and the person that had previously been the receiver is now the thrower. The jobs switch when the direction that the ball is being thrown switches. So that's all that we're really doing here with our acid and our base, is they're tossing that ball, that H plus, back and forth. And we call things that are donating those H's acids, but that means that what the acid is going to flip-flop, is going to switch, depending on which reaction that reaction is going, which direction it's going. So let's apply this to some chemical equations, because this is really what you're going to be asked to do with that knowledge when we see a chemical equation, is label our conjugate acid-base pairs. And these are always going to occur as pairs, so the first thing that I recommend you do is find your pairs. So we're going to find the substances from before the reaction and after the reaction that look almost exactly alike. And the one that stands out to most is the one you should start with. So here, the thing that stands out to me that looks the most the same is this H2CO3 and the HCO3. Those are going to be one of our pairs. The only difference between those two formulas is a single H. Now, the other two are also one of my pairs. So we always link together two pairs in each of these reactions, but just start by looking for the most obvious pair first. Now that we have these linked, then we're going to start trying to label our reactants as acids and bases. These are always going to be our plain old acid and base in some order, maybe acid, maybe base. And then our conjugates are always going to be on our product side. So looking at these pairs can also help us figure out how these things are acids and bases, whether they're donating or accepting an H plus. So let's focus on the H's here in our green pair. My H2CO3 has two H's in it, and after the reaction happens and it's become HCO3, then it only has one H in it. If I went from having two H's to one H, then I must have donated an H, and if this is an H donor, then that means that this is an acid. My next step would be to look at my other reactant and to make sure it's a base. You should always have one of each. But before I label anything else, I'm going to make sure that I do think this is a base. Because if I look at it and I think it's an acid, then maybe I was wrong with my first answer. So let's look at H2O. It is evidently becoming H3O. It started with two H's and now it has three. It must have accepted and gained an H from our other substance. So it is acting as an acceptor, which does mean that this, almost got that backwards there. This is, in fact, a base. Bases are our proton acceptors. So good, I've got an acid and a base here reacting, and now their conjugates are going to be easy. Because if we can remember, we always need to remember, the most important thing to remember here is that our acids, this green group, is turning into a conjugate base. They always switch jobs when it becomes a conjugate. And that means that our base from that purple group, our purple product, is going to be the conjugate acid. So those are our identified conjugate acid-base pairs. Now, in this next one, looking for the most similar standout groups, I see NH3 and NH4 look pretty similar. Only difference is an H, so those are one of my pairs. And then H2O and OH are the other. As we look at our NH3 turning into NH4, went from having 3 H's to 4 H's, which means this must have accepted an H plus from somewhere. and H acceptors are bases. So I'm hoping that H2O ends up looking like an acid, and it does, because it started with 2 H's, and then it ended with only 1 in that OH minus group. So this is an acid because it was a proton donor. And just like before, I can start following my pairs over to the product side because this NH4 started off as NH3, which was a base. When I'm deciding what kind of conjugate this is going to be, that means it's going to be the conjugate acid. And because that was the conjugate acid, or because it started off life as the acid, this must be the conjugate of the opposite, the conjugate base. Now, on this next one, I'm starting to look for my pairs, and this big crazy acetate group is definitely the most obvious thing that I'm linking together here. And even though I started by linking not the first substance, I am still seeing the same pattern that I was seeing before. And so I kind of want to caution you. Remember that we can have these substances written in any order. So it's not always going to be the first thing linked to on the reactant side, linked to the first thing on the product side. Here, my H2O, I would still link with the H3O. When we're linking our pairs, we always need to make sure that we're connecting the things that look almost exactly the same. The only difference between the before and after part of our pair should be a single H, either being gained or lost, accepted or donated. So I am going to go back to this original version, the way it's written here, and work this problem out normally. But I am going to ask you to work a couple problems, those last two that I don't have here. You're going to be working those on your own. And that is the first time you're actually going to see one that doesn't have this same kind of pattern in its pairs. So I wanted to caution you now to be careful when you're making your pairs down below. So let's focus on this H2O and how it's becoming H3O. It's gaining an H. It's accepting an H. So this is going to be our base. C2H3O2 is becoming just C2H3O2. Even though it still has some H's there, it's this first H that was at the beginning that is now not there anymore. So this had an H and it lost it. It gave it up. It donated it. So this is going to be our acid. And now green pair base becomes our conjugate acid. And our acid, purple pair, becomes our conjugate base. So as long as we remember acids turn into conjugate bases, bases turn into conjugate acids, and that we can find our pairs and connect them together and see how things are changing. We just have to be careful as we're looking at those pairs. We should be able to find our conjugate acid-base pairs pretty easily in this next set. So you go ahead and finish these up. And then if you haven't already, what we're going to do in class or have already done in class, the next place that we have to practice this idea is down near the bottom of page 5, where we have some reactions written out for us to identify those substances again.